2613. So the first thing that we are going to discuss, we are going to talk about the monotonic convergent theorem. Let's talk about monotonic convergent theorem. So what is monotonic convergence theorem? What does monotonic convergence state? So monotonic convergence theorem is state that any bounded monotony frequency of a real number converges to a limit so it converges to a limit. So in other words, we can write this in the other way. So the way we can write it, we can say it's the same definition. This is a definition of monotonic convergent theorem. So we can still state this theorem as if we let our AN be a sequence of a real number be a sequence of a real number that is bounded and either increasing or decreasing then the sequence converges. Converges to a limit which we can denote it as L. Which is also a real number. So this is the definition of the monotonic convergent theorem. So now when you have this part of definition, you will note that we talked about the sequence is sequence that is increasing or decreasing. So the sequence that is increasing, decreasing, and the theorem, it also states that the sequence of a real number that is bounded. So when it says bounded, then which means the sequence that we are going to work with is either is going to be bounded, above. When a sequence that is bounded above, then it means that the sequence is going to be increasing. It's going to be increasing, and we're going to talk about the sequence that is bounded below. So the sequence that is going to be bounded below, it will mean that is going to be a decreasing sequence. Then, if the sequence is bounded above, it means that it's going to converge to its supremum. Premium. And if the sequence is bounded below, it means that according to this sequence, this theorem of monotony, then it's going to converge to what? It's going to converge to its infimum. So now when you have this, so when you go into proof, you are going to be asked to prove a sequence that is either it converges to any, it can be any real number, which it can be infimum or supremum. So, but sometimes the question, it won't really ask you be specific that is going to be infimum or supremum. They can tell you that a sequence of an is going to, it converges. It's a monotonic sequence that converges to 0. So you will have to prove that indeed it converges to 0. So the following steps that I'm going to give it to you now, they are the steps that you always use. So I'm just going to give you the only one part when we are talking about the increasing sequence. So these steps, you follow them every time when you answer any questions. So if we have a sequence, suppose an it's a sequence is an increasing sequence and is bounded above and is bounded above and defined, let's say it's defined or defined as L equals to infimum subpremium of an. This is which whereby n is element of natural number or n. Then we have to prove, or you have to show. I will just use as a proof. So in order for you, the steps that you follow when you prove this statement is equivalent to all the questions that you are going to be doing. It's either in your question papers, you follow exactly the same way that I'm going to be showing you. We must show that in this one, we are going to show, that an approaches L. So given E greater than 0, by the definition of supremum, there exists n such that L minus epsilon is less than an, the capital letter N, whereby L, this one is capital letter N, whereby is less than L. So since an is increasing, since an is increasing for all n element greater than n, we have an which is less than or equals to an, small letter n, which is also less than or equals to L. Thus, L minus E epsilon is going to be less than an, the capital letter N, which is less equals to an, which is less than or equals to L. So now for all, this is for all n greater than or equals to n. So now this implies that what I just wrote here, it implies that the absolute value of an minus L is less than epsilon for all n is greater than or equals to n, capital letter N. Therefore, an approaches L. So now the first step that I've written here, I'm going to try to explain the few things. We have stated that this statement here, it implies this way. So why did we say this applies this way and we wrote this L minus an minus L is less than epsilon coming from this statement? So we wrote it because of when we have, if we can take L minus E, which is less than, we take it as less than, this less than here, we, instead of taking an, because this is less than n, which is less equals to an, we can say is less than an. So I will take my value of L, I will take it the other side. When I take the value of n to the other side, when I take my value of L to the other side, this is L here, it's going to say minus E is less than an minus L. So if I change this, I multiply everything by L here, it's going to be E is greater than an minus plus L. This one, it will change to negative plus L. Negative plus L. So if I change back, or if I don't do anything here, let's say I didn't use these steps, I can rewrite these statements as an minus L is the same as greater than, because of this letter there. So if I introduce absolute value and I introduce absolute value both sides, then my question here is going to be saying absolute value of an minus L, then this sign is going to change to be less than, then absolute value of this, because this epsilon is a number, it will be E. So absolute value of a number, -1, is the same as 1. So it's going to say E. So, but because of introduction to the absolute value both sides, we change the sign. The 10 is going to be less than epsilon. So that's how we came up with this conclusion, that this implies that epsilon, absolute value of an minus L, is going to be less than E for all n natural number. So now we'll go to a question. So the first question in your assignment, I think, is the last question, which state that use the monotonic sequence theorem to prove that an, a sequence called xn, equals to 1 over square root of n, converges. It converges to converges to 0. So the first thing in this, I'm going to read it again. It is use the monotonic convergence theorem to prove that xn, which is equals to 1 over square root of n, converges to 0. The first thing that we were not given here, we were not given if this sequence is increasing sequence. It's an increasing or decreasing sequence, or decreasing sequence. Then the first step that we'll have to find, we have to know if this sequence is a decreasing sequence or is an increasing sequence. So according to monotonicity, for n, which is greater than m, which is also greater than 0, we have in this sequence we're going to have, we have xn, we're going to have xn, our xn minus our xm, which is going to be equals to 1 over square root of n minus, let me erase this negative here. All right, it's not erasing, then it's fine. We know that it does not mean anything. Then minus 1 over square root of m. So this is going to be equals to, if we take the lowest common multiple of these two, we are going to have square root of n square root of m, which is equals to, if you divide this by this, you're gonna left with square root of m multiplied by 1 minus square root of n. This is going to be less than 0. Less than 0. Thus, because this is less than 0, it's going to be less than 0. Thus, xn is a decreasing. It's a decreasing sequence. So now we know that it's a decreasing sequence. So now we have to check also the boundedness. Boundedness. So checking the boundedness, we are going to check about the, if it, checking about the boundedness, we are going to check if it's an increasing, if it's a supremum, if it's bounded above or bounded below. So by checking that, for all n which is greater than 0, we have, for all n that is greater than 0, the n that we're talking about, remember, is this n here. So for all n that is greater than 0, we have our xn we have xn, which is equals to 1 over square root of n, which is less than or equals to we can substitute, because we can substitute. Remember, we are working with a real number. We can decide to substitute 1 in this square root of 1, which is going to be equals to 1. It gave us 1. So now, therefore, we are going to say for xn, that approaches L, the L which is greater than or equals to 0, we must show that we have to show that L, this L is equals to 0. That is the purpose of proving here. We must show that this L is equals to 0. Then now to show that, suppose by contradiction, that our L is greater than 0, then there exists a positive number there exists a positive in number or a positive integer. You can just use or integer. N such that for all n which are greater than n, we have zero. Now we are using that proof that I was showing you, but I was showing you in terms of increasing the first time. Now, because it's a decreasing, if I say 0 is less than, is greater than, here I'm going to say 0. If I say xn is less than, for increasing, here I'm going to say our 0 is going to be less than xn, which this is less than L, less than or equals to, which is less than L over 2. So now when I say that in particular, for n to be equals to our n, small letter n, to be equals to n, we have xn, the capital letter N, to be equals to 1 over square root of capital letter N, which is going to be less than L over 2 for all n, or for all n, okay, which is L over 2, not for all. We must not write for all. Let me just write this. So now when I have this, if I square both sides here, I want to know what is n. If I square both sides here, if I say 1 over n, square root of n, and I square, I'm going to have less than L squared over 4. Then this sequence is going to give me 1 over n, because square root of n, if you square it, is going to, the results are going to, is going to be n. Which is less than L squared over 4. So if I swap these two in order for me to get n, then I'm going to get n is greater than 4 over L squared. So when I get 4 over L squared, this contradicts our theorem. So this is going to be, it will contradict our theorem. It will contradict our theorem. So let me just create a space here. So that will contradict, but this will contradict the fact that n is a positive integer. So due to this contradiction, we conclude that L equals to 0. Hence, the sequence xn, which is equals to 1 over square root of n, converges. Converges to 0 by what? By the monotony convergent theorem. So exactly from the starting point, when I started for showing you that this sequence is a decreasing, until this, it proves that that question, the last question of your assignments. So if you check there, I just checked a little bit with the question that you sent me. So those questions there in 4.4, the one like for the answer for a friend of yours, which said that according to monotonic convergent theorem, if a sequence is decreasing, is bounded below by an infimum, it will converge to the infimum. That's true. Now xn equals, that is a sequence of a positive terms for all n elementary natural number. Also x1, it says equals to 1, which is fine. X2 is going to be equals to 1 over 2, square root of 2, which is okay. Then x3 is going to be, which is fine, so and so on. Clearly, we can check that x1 is greater than, you said x1 is greater than x2. So x1 is greater than x2 is true, and x2 going until xn, that statement is clear, is fine. That is, xn is a sequence of monotonic decreasing function terms, which is true. I also prove you that is monotonic decreasing sequence, and lower bounded is 0. So the lower bound is 0. Okay, so now he said the lower bound is going to be 0, but we have to, okay, it's fine that he's saying the lower bound is going to be 0. Then let's keep going. So if you check there, it says, so infimum of xn equals to 0. That's fine. Therefore, by the monotonic convergent theorem, limit when n approaches infinity, limit when n approaches infinity of xn equals to limit when n approaches 1 over xn, which is equals to 0. Okay, so the problem part with this proof is fine. His proof was okay, but he missed one step. He missed a step to prove that the lower bound is indeed 0. So he must also prove that the lower bound is 0 in this one, in that question, in his proofs. So proving that the lower bound is 0, it will make this proof to be a very complete. So what he just said, that the limit is 0. So it does not, he must also show that the lower bound is 0. So he didn't really show that the lower bound is 0, but he did show that this is a decreasing sequence. He showed that. I'm happy with that. But that the lower bound is 0, he didn't really show that. But the proof that he did there is fine. So you can decide to choose to answer using his proof, or you can also answer using this proof that I gave it to you. So do you have any question?
No.
All right. So this is, you can choose between. So I'm going to send you this one. You can also check, you discuss, if you have time to discuss with him, you can also, you discuss about it. How did, like, you will show him also, but it's more of the same, just that I prove it in a contradiction. It's a converse. I use the converse. So you cannot write both of them in when you're answering. It's either you write one, the one that he sent you, or the one that I'm showing you now. So this is exactly the things that I wanted you to know today. So if you don't have any question, we can maybe check one of the questions with those few questions. So I think the other questions, they're clear because I checked them. They didn't, I even showed you that they are fine. You can copy them with them. There is no problem. You did them correctly. So let me just randomly open any question paper. Let me see. I see the one, okay, this is assignment 2022. Let me open this one for 2018. I will try to check. I think I have the question paper for this module for last year, for 2022. I will try to check it. So for the 2023, I'm not sure if we have done it before. Consider the functions. Let's start. This is the same, more of the same questions. It says question number 2 says proof from the first principle that the sequence an, which is 6 minus n squared over 2n squared plus 5n, it's an element of natural and converges. So in order for you to prove this, I think, have we done this question? I don't think so. We never done this question paper. So in order for you to prove this, is simple. We use the same process that we did before. Our an equals to 6 minus n squared over 2n squared plus 5n. Let me check, is 5n. So we have to prove that this sequence converges. In order for me to prove this, that sequence converges, which means we get the limit when n approaches infinity of an, which is going to be equals to the limit when n approaches infinity of this sequence, which is 6 minus n squared over 2n squared plus 5n. Then we check the one with the higher degree of polynomial, which is here we have n squared. We divide everything by n squared. If we divide everything by n squared, we are going to have limit when n approaches infinity of 6 over n squared minus n squared over n squared divided by 2n squared over n squared plus 5n over n. So, but n squared, but when you are doing it, some of the steps, if you want to eliminate them, you can eliminate them. It's just that I'm showing you so that you can see how we get the answer. Then limit when n approaches your infinity. We know that limit when n approaches 6 over n squared, 1 over n is 0. So here we can say, if you want to rewrite it properly, sometimes if you are rewriting it properly, but it's not really necessary, but you can show it. You can say limit when n approaches infinity of 6 over n squared minus n squared. But now, instead of n squared, we can see that n squared minus 1, n squared divided by n squared is going to give us 1. So we can just write 1 there over, this is the same as limit when n approaches infinity of n squared divided by n is going to be 1, which means we're going to left with 2 plus 5 over n. We know that limit when n approaches infinity of 1 over n equals to 0, then which means this one here is going to give us a limit when n approaches infinity of, you can take out 6, is the same as 1 over n squared, minus limit when n approaches infinity. Instead of 1, I can just leave it at that, but or I can write 1 there is fine, over limit when n approaches infinity of 2 plus this 5, we can write it that side with a limit when n approaches infinity of 1 over 5, 1 over n, then this is going to be equals to, I'm going to erase this part, going to be equals to, if we check here in our limit, we know that this one is going to be 0. So we're going to have 6, 0 plus minus 0 minus 1. The limit, this one is going to be 1 over, this is going to be 2 plus, this one is going to give us 0. Then the answer is going to give us minus 1 over 2. So which means this sequence, because we got that our L is equals to what? Equals to minus 1 over 2. It means that this sequence converges. So this is how you show that this sequence converges. So a sequence that converges, it must apply, it must have a limit when n approaches infinity of a sequence. It must be equals to L. So it implies that this an converges to L whenever n is an element or is greater than or equals to n. So that's how you do it. Do you have any problem with that question?
No.
So which means for starting today, I'm going to be assuming that any question which with this question here, you won't have a problem with it because we have done many questions based on this kind of a question. So the other one says, give an example of a sequence an, bn such that an and bn both diverges but an multiplied by an converges. So in this one now, we have to search. We have to give an example of two sequences that those sequences are divergent, they don't converge. So what is a sequence? A sequence that diverge, it can be a sequence that it just keep going. It is non-stop. So we can first find one of the sequences that converges. If I have a sequence That is like, for example, I'm gonna give you first in terms of number. If I have a sequence that it can say 2, 4, 6, 8, and 10 going onwards. This sequence you can see that it does not converge. So, but if we find the formula for this sequence, we can see that the difference So I'm back. I just changed the devices. So let me see. Let me make myself. I'm gonna log in now with another device. I just want to make some few changes first so that
Do
I
you
can.
still have do you have the recording?
Yes, the recording is there. Normally, if when it switch off, it normally save the recordings. So I'm gonna send you, and then we also have yesterday's recordings, né? I'm also gonna check it and send it to you. So
Yes,
just wait for me. All right, here now. Can you hear me now? So
Yes.
for this part, I'm not sure if because I can't combine those two, but it's just the few things that we have to make it clear. So that question, there we have to find two sequences. So the sequences that we have to find, they are sequences that they diverge, and when we multiply them, so we have to find a sequence that diverges. So I was showing you with one of the sequence, like we have, I wrote the first one, it was 2. Okay, let me clear. 2, 4, 6, 8, 10, going upwards. So we found that the difference here, you can see that the difference is 2. So which means our AN, here we can say equals to 2N. So whenever we put 1 here, it's going to give us this sequence. So this sequence is divergent. It's a divergent sequence. It's a divergent sequence. So let's check another sequence again that is also divergent. If we check, if we have a sequence that is 1 over n, 1 over n, this sequence we can see that the more we substitute 1 here is going to be 1, 1 over 2, 1 over 3. So this sequence is convergent, it won't be divergent. So let's check another sequence that it can also, let's say, let's check another one. The other one which can check, maybe it can be the one for n squared. This n squared is going to be convergent also. It's going to be divergent. Because if we substitute 1, it's going to be 1, it's going to be divergent. But when you combine both two, if this one is Bn, it's a sequence of Bn. So if we combine with this one, multiply these two sequences, they are still going to be divergent. So which means I'm going to check a sequence that is can be 1 to the power n. So a sequence to 1 to the power n, if we check it, this sequence, no matter how we give it, it's going to be remaining at 1. It won't work. So if I check a sequence that is negative 2n, negative 2n is going to be a negative number, but when we multiply these two, it's going to be negative 2n squared. So it won't be divergent. So in order for us to check that sequence, we have to find a way. If I have a sequence an, the way the book is saying, and bn, so these two sequences, they must be divergent. They must be convergent. So in order for me to have such sequence, so I'm left only with 1. Let me try to check how I can. We have negative 1. Okay, so now in order for you to answer this question, I'm gonna show you help you show you another trick. So we know I taught you about something about the p-test. If you remember about the p-test, in p-test we determine that if you have your p, if you have a p, what's wrong with this mouse? Okay, so if you have a p and your p is greater than 1, we know that the sequence is going to be divergent. And if p is less than or equals to 1, then your sequence is going to be convergent, divergent. So we can take a number, we can take a sequence that our bn is equals to 1 over n to the power negative 2. So when we take that, we know that this sequence, okay, let me just change the mouth. We know that this sequence, is to the power 2. So we know that this sequence is divergent. So if now we combine 2n, we multiply both sides with 1 over n to the power negative 2. This sequence now, because it's 1 here, is going to leave this one as 1 over to the power negative 1. So we can make our sequence to be to the power 3 here. Even if we put it to the power 3, or we can just write, instead of n here, let's eliminate these 2. We write our an equals to n to the power 3. So the sequence a equals to n to the power 3 is going to be a divergent sequence, because it will never, if we put 1, it's going to be 1, put 2 is going to be 2 to the power, it's going to be 8. It's going to be an increasing sequence. It will never stop. It's going to be a divergent sequence. So now, if we let this sequence, our an equals to n to the power 3, and our bn equals to 1 over n to the power negative 2, both these two sequences, they are divergent. They are divergent sequences. So when we multiply them, it's going to be n to the power 3, which is equals to 1 over n squared to the power negative 2, negative 3, negative 2. Then they are going to give us equals to n. So n is still divergent. So we didn't manage to get a convergent. So it's going to be divergent. So we must make sure that those sequences, when we get them, they must be in a form of a divergent sequence. So this one still is going to be a convergent sequence, because if our n is equals to 1, if it's starting at 1, it will never stop. So this question I'm gonna try. So you can just try to get one of those questions by testing them. So when you get them, then maybe I'm gonna try to get also those 2 questions. Then after when I get them, then I'm gonna send it to you which ones you can use. But you can also try them. It's just a matter of testing until you get those 2. Then after that you remember them. So that if you can get a question like that, then you must remember. But I can just give me 2 minutes. I want to check them for you, because I know that I can find them quickly. Or are you also working them out?
Okay, are you still here? Hello? Mr. Whiteboard. Hello?